In this task we have a circuit with an inductor in it and a switch. And this switch is opened in the moment t equals 0. And we are asked for the time function of the current through the resistor R2, and we are asked for the voltage drop at the inductor. Okay, let's go. So let's analyze the behavior of the circuit after opening the switch. Okay, and when we open that switch, everything is left is only this here. And you see we have two elements in parallel, and therefore there will be the same voltage drop at both of them. And if you deal with a circuit with an inductor and you want to calculate the transient behavior, you should always take the current at the inductor into account for your calculations. So let's introduce this current here and work with that. We have two unknowns, the current and the voltage. That means we need two equations, and those are our element equations. So we have the element equation of the inductor and we have the element equation of our resistor. And when we want to use the terms UL and IL, you see the voltage is directed upside down and the current flows upwards. And that means voltage and current are defined in active sign convention, but the resistor is a passive element, and therefore we have to take that into account by adding a minus into Ohm's law. And now we have two equations and we can merge them into one. This is already a differential equation. Let's sort it a bit. I bring everything on one side. And now remember from the lecture, there was only one differential equation where we know the solution of. And it looks like this. So we need a time constant tau in front of the time derivation of the value we are looking for, plus the function we are looking for itself, and all this can be equal to a constant. And then we know a solution for that. And that means to bring it to that form, we should divide by R2, and then our equation looks like this. Okay, that is the differential equation that describes the current behavior at the inductor. And we know that this here is the time constant tau. And now we know the solution for that. It's here in the lower left box, the last line. Okay, so we know this here is the solution, but we still have these unknown constants K1 and K2 in it. And we get them with the so-called boundary conditions. So we can say when we wait long enough, our t goes to infinity, and that means e in the power of minus infinity is 0. And therefore, from a mathematical point of view, all that is left from our equation is the constant K1. Okay, and now let's have a look to our circuit. We open the switch and we wait for a very long time. And the current will flow out of our inductor, and the energy stored in the inductor will be transformed into heat in the resistor. And that means if we wait long enough, the current will go to 0. Hey, we have our first constant. Okay, and in the very moment where we open the switch, from a mathematical point of view, we have e in the power of minus 0 divided by tau. So e in the power of 0 is 1. And therefore, from a mathematical point of view, it's just K1 plus K2. And now we look back to our circuit. The current at an inductor can't change its value rapidly. And therefore, in the moment where we open the switch, the current has the same value as before when the switch was still closed. And therefore we can have a look at the circuit when the switch is closed, and yeah, the inductor behaves like a short circuit there. The switch was closed for a long time, and the current in the inductor has its final value for that condition, and therefore the inductor behaves like a short circuit. The current is just U0 divided by R1. And now we have everything. The slide before we already found tau, it was this here, and therefore we have the time function for our current in the inductor. But wait, we were asked for the current in the resistor. And yeah, have a look, it's the same current, it just flows into the other direction, and therefore IR2 is orientated in the other direction, and therefore it's just the negative current here. Okay, let's draw that. When the switch was still closed, the inductor behaved like a short circuit, and therefore all the current coming from the source flow through the inductor. And that means the current in the resistor was 0. And after opening the switch, the current from the inductor had to look for another path, found it in the resistor, and flew in a circle through the resistor. And therefore, the current in the resistor jumped from 0 to the maximum value of the current in the inductor. And after that, it decreased, described by this exponential function, and therefore we can use our time constant tau to indicate the slope in the beginning, and then we draw an exponential function. And it looks like this. Okay, and then we were asked for the voltage drop at the inductor. Okay, we know the current at the inductor, and the element equation says that the voltage is L times the time derivation of the current. Okay, time derivation, yeah, we have an exponential function. Derivation of that is the exponential function itself, but we have an inner derivation in that function, and therefore the total voltage will look like this. Okay, and we can clean it up a bit, and then it looks like this. Let's draw that. In the beginning, when the switch was closed, the inductor behaved like a short circuit, and therefore there was no voltage drop added. And when we opened the switch, the current from the inductor found a new way through the resistor, and there a voltage drop occurred, and resistor and inductor were in parallel, and therefore the voltage drop at the inductor is the same as at the resistor, and yeah, it's this here. And then again, the current decreased, described by an exponential function, and it's the same here. So we can use tau, and we can draw our exponential function describing the voltage drop at the inductor.